Okay. Good morning, everybody. I will talk. I'll continue talking about application of amenable actions, and one of the most important application is to rigidity. This is really maybe the most, in my view, it's the most important one. What's the setting? So we have a countable group acting amenably, and we assume so gamma countable group, and X mu probability space. Mu non-singular. Okay, non-singular action. It was the setting we had. So now we assume we have also an action on gamma on the compact metrizable space. So continuous action on compact, I don't know, but okay, metrizable space, but it's probably not important. And here's the application, a proposition, or it's more proposition than theorem. This is something first appeared without giving, I mean, there was no notion of amenable action, but still the result in some context, in a special situation, was proved by Furstenberg, and then used by Margulis and Zimmer. And what does it say? It says there exists a measurable mapped phi from X to, now one would like to have to Y, but it goes not always, it's not always true, but it's at least the probability measure, which is equivariant, gamma equivariant. So that means, I say it's precisely for almost every X. In X, we have that phi of X, gamma X, is the image of phi of X for every gamma in gamma. So usually it's used in the following situation. That's how it's used by those people, Furstenberg, Margulis, and so on. So first, you as X, you usually take a boundary in the sense which Hannah told us about. Maybe the Furstenberg boundary, but it doesn't have to. I mean, if gamma is, let's say, a lattice in a semi-simple Lie group G, then you would like to take G mod P or something like that. And Y would be something like, in this situation, G mod Q. And sorry, no, what I want to say is maybe, example where you want to apply this is X boundary, for gamma, for probability measure gamma, which was denoted mu by Hannah, but the mu for me is, I should have taken actually nu, because the boundary is usually, no, okay. It's too late to change notation. And this is where you, so in this kind of situation, and for instance, if you have a map phi from gamma to some other group, lambda, it could be, I mean, okay, if you have just a homomorphism like this is how, why it's used by those people, then this gamma acts also, this lambda will act on a boundary. I mean, it's Poisson boundary or whatever. And then you get something from X to probability space of Y boundary or whatever, boundary, a boundary for lambda. And so this map gives you an action of gamma on this boundary. So gamma is acting on this boundary through via phi. And now, if you can, and that's what's happening in this super rigidity stuff. So Margulis is using this super rigidity theorem, or normal subgroup theorem also is really using this. And now you have to upgrade this to point measure. So you have here a probability space, but then you have to somehow to work, but that you can do, and you get to map from X. Sometimes, sometimes you get under some assumption for some Y, or get map, equivariant map from X to Y. And this is, of course, a wonderful thing. I mean, you can do now. I mean, if X is G mod P, for instance, in some situation, and Y, gamma is another subgroup, Lie subgroup H, then it could be, this Y could be H mod pi prime or Q or whatever. Then you get really, I mean, this is the beginning of the, or at least the crucial step in super rigidity theorem, or normal subgroup theorem, Margulis. Okay, that's this tells you why it's so important. I mean, why amenable action are important. Maybe I should give you a proof of a hint. I mean, no, a proof. I mean, no, it's really a proof. So we have our expectation. And now we want to construct something from X to the probability measure on Y. So equivariant expectation. And how do we do this? So if you take point X, you can define a functional. Oh, first, maybe, oh yeah. No, before I do this, I have to do something else. We have to relate the continuous function on Y to somehow to X to the to n infinity. To the bounded function on gamma, sorry. So we fix some point. And the continuous function on Y, we can map them to the bounded function on gamma by simply, for every function here, we can associate, we looked at the orbit and restrict the function on the orbit, on the Y naught orbit. So it's f of gamma Y naught. Does it make sense? Yes. So we call this, I don't know, tau, this map. And now we have somehow, it's not exactly, but embedding, but anyway, we map the continuous function. And now we define, so if we have X and X, we define a measure as functional phi x functional on Y, which is the okay, by, for every function, continuous function on Y, px of, what can we do? What we can do is we extend the image of f under tau to bounded function on this here, trivially, and then apply t. So I call tf. So the extension, trivial extension, and we evaluate this on x. So this is a number, and so tau, of course, of x gamma is tau of f gamma. Okay, and so this is positive functional, and phi x is positive, and phi x of 1 is 1. So get by Riesz theorem, phi is probability measure, or corresponds to probability measure. Phi of f equal d mu x for some probability measure mu x on Y. And we have just to check that, so we constructed, so this is the check that the probability measure mu of gamma x is exactly the image mu x. Okay, this is of course the, how can it be? The only thing you're going to use, of course, the equivariance of this expectation. Okay, so this is the proof, and there is probably a question you would like to ask at this point. No. You see, amenable action gives rise to such a equivariant map always. Sorry? Yes, the converse. And the converse, I don't know. I think it's but no. So if you have an action on gamma, if you always have this property for any compact gamma space, if there is always such boundary map, how they are called. I mean, even if X is not always a boundary, but I don't know. Anyway, as far as I know, it's an open problem. But okay, should I say something else to this? No, I think it's. I can only emphasize the importance of this this proposition. I mean. And it really first appeared, I mean, this idea is by Furstenberg on for Poisson boundary. I mean, context of most groups are exact. Why is it the same?
Yeah, probably not the
When you obtain amenability, then for X?
I mean, if you have the Zimmer amenability on a factor, or you have amenability on the
I don't know. We should talk about it. I don't think. Okay, maybe. Yeah. Okay, so this is application. So the next point I wanted to treat is amenable groups are, as we saw them. I mean, this Hulanisky writer property is actually can be formulated by saying that a group is amenable, gamma is amenable if the trivial representation is weakly contained in the regular representation. It's exactly is equivalence. And in the context of amenable action, there is a spectral characterization, and it's not characterization. I will come back to this point, but at least spectral implication. Okay. So spectral implication. For the Koopman representation. I remind you that so gamma, so if you have a non-singular action, then the Koopman representation is defined on L2 of X nu, sorry, a unitary representation, L2 of X nu by gamma of Fx. So here we have the random Nicodim derivative. We saw this with Hannah. So X F of gamma minus 1x. We have to take here the square root because we want to have, we are working in L2, so we want to have a unitary representation. Is unitary representation. By X. called Koopman representation. And okay, and yeah, here's a theorem. Due to Gabriele Kuhn, 1998, something like that. 4. Assume that gamma, the action, is amenable. Oh, maybe before I stated and then I defined the notion. Then this Koopman representation is weakly contained in the regular representation. And okay, weak containment is, as the name says, weak notion of containment. So it's not subrepresentation, usually not, maybe never, except in some very special cases. But it's weakly contained means, so recall, if for two representation, for representation, unitary representation, pi and rho of gamma, not have to, we'd say pi is weakly contained in rho, and we write pi rho if you can approximate every matrix coefficient of pi by matrix coefficient of rho. That's not exactly, I mean, it's not, that doesn't work always. One has, I mean, it works for reducible representation, this definition, but you will have to somehow to modify this. If you can approximate every metric coefficient of pi by sums of metric coefficient of rho. So if for every, let's say, formulate this way, every h and every epsilon, we have to, yes, there exist finitely many vector in K such that, so the sum of rho gamma minus is smaller than 0. So you can approximate every metric coefficient by sums of pi by sums of metric coefficient of rho. And equivalently, maybe, but okay, this much shorter, but in the usually when you work with these things, you have to usually to use this one. But anyway, I mean, the shorter version is that for every, sorry? Oh, yeah, it's right. Yeah, yeah, you're right. If for every f in gamma finite, and for every there exists such that this is true for every gamma in F. Okay, you have to do. Okay, you have to have it. Yeah, I mean simultaneously on finitely many points, and equivalently is for every let's say I don't know maybe function L1 function, but it doesn't matter. Pi the operator norm of pi f is smaller than the operator norm of f of rho f, where of course pi f is the operator sum of f gamma pi of gamma. This is this bounded operator, and okay, and the same of course for rho. So this is of course shorter, but usually you don't work with this definition. It depends, but I mean, so I explained the. So that means that you have that every matrix coefficient of this Kopman representation can be approximated by. And here we will see. I don't know whether it's some or. Okay, we will go. We will. Okay, so proof. Actually, I'm going to give you the proof of Kuhn's theorem. We start with the writer Hulanisky writes a characterization of amenability. There exists a sequence of L2 function on I mean positive, it doesn't measurable with the L2 norm, I mean with respect to gamma, sorry. So that means we have this here, gamma. For mu, almost this is 1, and the invariance property. I mean, okay. Delta minus 1 x, delta minus 1 gamma minus x gamma. What is it? Is it, yes, this one square gamma, and this should be true if you test this, average this with an L1 function on x. This should goes to 0 for n infinity. So this is true for every mu, almost every x, and this is true for every function h in L1 of x, and for every delta in gamma. So this is the Hulanisky writes a property or characterization or whatever of amenability. So we are going to use this to approximate this matrix coefficient by of pi x. Going to use this, and so we fix. I mean, we take a metric coefficient. So that's a metric coefficient. That means that a function in L2 of x, and the metric coefficient we want to approximate a metric coefficient by x f. Okay, by something in the regular representation. So okay, and the function which are the sequence we need define Fn. So there's going to be a function on, should I introduce? Yes, two variable. Fx. So these are functions on L2 of x. With here I take the counting measure, and even more. So this is in L2 because sorry. Yes. Yes, because this is in L2, and you see you can. I mean, if you sum over the integral over x and sum of gamma, you see this is finite, and even you see that this is the norm is actually. I guess it's the same as the L2 norm of F. Probably not important, but yeah, it's not important. So you can even compute this, and you see this is I mean, because of the first property, these are if you squares the and you sum over the gamma disk and you get always one. So so this you can okay, but this is certainly not important. But what else? Now I claim that okay. No, we are here in the. This is the same thing as L2 of x as a product of this new Hilbert space, and so in this Hilbert space, I can look at the tensor product. Or the representation is, or the representation is realized on this tensor. I prefer to work with this at least for this proof by simply gamma of function. Oh, now I have to probably put a delta here. This is what is it? Pi x of so f is going to be shifted gamma, and here probably what could it be? Px of delta or delta minus one. I don't know whether this is the probably. No, actually not. Actually, you have no. It's I'm writing this. I write the right formula. The right formula is the following: is or the complete formula is d star. So I'm writing this explicitly. My representation. So the formula is this. So this tensor product, if you translate this into, which is realized, if you translate this in this as function on x times gamma, you get this formula. Okay. And now we take delta in gamma and compute, and we compute actually the matrix coefficient. You, I guess you guess what's going on. This function are in this L2 of x times gamma. On this, I have this representation I'm going to compute the matrix coefficient of this representation, pi tensor lambda for this Fn. So I have to compute this. Fn. So this matrix coefficient, and hope this has something to do with metric coefficient of pi for F. And this is indeed what's happening. So I have to, maybe I should make some place here. So this is now really just an easy computation. I mean, once you have the idea to define this Fn's and to look at this thing, you're done. I mean, because if things work, I mean, that's what they do. Sorry, here's delta. So this is the sum. So I'm just using the definition pi x. Yeah, delta Fn on x gamma and Fn x gamma and d mu x. So this is okay. And this is, I'm using this formula here, x gamma and then d random Nicodim derivative, square root, and then Fn delta minus 1 x delta gamma, and then Fn x gamma d mu x. Okay, and here I'm using now the definition of Fn. Fn was psi n x gamma times F. And oh, sorry, here's the delta minus 1 x delta gamma. And I have f of x here. I have f of x here also. I can, it has nothing to do with the sum over gamma, so I can put this in front of the sum sign. Delta inverse, yes, sorry, yeah. I will make many such mistakes, but which are easily, I hope, easy to correct. But so here I have f of delta minus 1 x. It looks already like the Koopman representation. And here the sum over gamma psi delta minus 1 x delta minus 1 gamma x gamma, and here d mu of x. So if I call this function h, you see this is a function in L1 because this is in L2. This is in L2. Product is in L1. So yeah, we have probability space. It wouldn't have been a problem, but it just tells you that you are on the right track. I mean, somehow it's things fit together. So A is in L1, and what is H d mu x? This is you see, if you integrate this, you get exactly the matrix coefficient delta of FF. So this is, you get this matrix coefficient. And now you have this term, and this you would like to have it going to 1. But this is the case because, you know, this is somehow, if you compute, you know, this by this property here, if you compute the square here, you have this square here, this square here, but this is 1 if you sum over gamma, and you have the product twice or whatever, but then, so, and the whole thing is going to 0. That means this product, the sum of the products goes to 1. So this, I mean, it goes to 1 if you integrate without over x. So hx. Okay, and so it doesn't go to 1 pointwise, but this goes to 1. This goes to, sorry, what did I say? Yes, this goes to 1 by, sorry? Oh, yes, it's integral of h. Yeah, that's a good thing. by star, yeah. I was a little bit confused. Yeah, you're right. That's actually what I want, what I would like to have. So what did we prove? We proved that actually x that the Kopman representation is weakly contained in not exactly the regular, but this here. And now this is a well-known fact that that the regular representation has this absorption property. It's got a big name, Fels absorption principle, but it's I guess everybody is used of that. No, I will formulate this. This is actually a hence also hence pi is weakly contained in regular by Fels absorption principle. What's called Fels absorption principle. It says the following: if you have, I mean, by unitary representation of any locally compact group, a locally compact group, then if you tensor it with the regular representation, this is equivalent, actually equivalent to a multiple. This multiple is given by dimension of and the proof of this is simply you can realize pi as on and this multiple on L2 of X, no, not X, on L2 of GH on this Hilbert space by pi tensor gamma of G F, and X is G minus 1 probably, and F G minus 1 of X. And then this multiple of the regular representation on this space is simply Fg minus 1 X. You get the multiple of the regular representation. And you have a unitary which intertwines these two representation, U L2 of GH, L2 of GH, which is defined as follow. For a function f, you associate a function defined by f of x pi x minus 1. No, sorry. Yes, I think this is what it works. It's probably, I don't know whether, I think the minus 1, you have the minus 1. Where you don't have the minus 1 is here. And okay, so this is a unitary isomorphism. And which intertwines intertwining the two representation pi, and so this is of course you have just to check, I mean, the formula. That's not nothing. So it's got a big name, but it's actually a very useful fact. I mean, that's and we are done. You see, we because if something is weakly contained in a multiple of representations, so weakly containment doesn't care about multiplicity. So two representation, one is weakly contained in the other. A multiple of the first one is weakly contained in multiple of multiple of the second one for any multiplicity. So it doesn't care. Okay, question about this? Yes. Sorry? Is it only one? Yeah, that's a good question. Thank you. The answer is no. It would have been nice actually to have a characterization of amenability through this property. Actually, unfortunately, the answer is no. So the condition does not imply amenability of the action. Here I give you a counterexample. A counterexample due to Claire Amontaram. Anyway, no, I mean, it's not completely true. I mentioned something, and the beginning was due to me, but they had I mean, okay, I will tell you anyway. So part of it to me and part to her, but anyway. And that's the following. And this is the following example. You take, okay, we take X equal SL3R, this space, SL2R. SL2R embedded as, I don't know, I mean, as probably maybe this way. It doesn't matter actually. And we take, yes, mu gamma, sorry, SL3R equivariant, quasi-invariant measure. So there is only one, actually, only one up to equivalence class of measure probability. Measure on X. So the Bekka measure, if you want, and you take gamma SL3Z. Then Px, I will write Px restricted to gamma, is weakly contained in regular representation, but gamma on X is not amenable. I'm writing Px. Px is actually, you see here in this case, the Kupman representation is actually a restriction of the Kupman representation is defined on SF3. L2 of X. So I'm mentioning this because what you want, what you prove is actually, in fact, this Kupman representation of SF3R is weakly contained in the regular representation of SF3R. And this is somehow really a curious example because you see this Kupman representation is actually is equivalent to induced representation of SL2R to SL3R, quasi-regular representation. And this is unusual. I mean, for discrete group, if you induce the quasi-regular representation of subgroup which is not amenable, is never weakly contained in the regular. So quasi-regular representation of a subgroup for a discrete group is amenable if and only if the subgroup is amenable. And here you have an example where the strange thing is you induce from a subgroup which is not amenable, and or you look at the quasi-regular representation of a subgroup which is not amenable, and you have something which is tempered or weakly contained in regular representation. This is unusual. And this is at the basis of the fact, I mean, of this fact here. And okay, and so you have to do some work to see that gamma is not amenable. Actually, what's not clear and open is to characterize what should be added to this condition to have amenability. Yeah. Sorry? Yeah, but this is not very. Yeah. Yeah. You're right. Yes. I mean, Claire had thought about this question. And, yeah, there are some indications. So I would say, okay, she deals in her paper with the converse. But okay. Should we have a break? Yeah. It's time. Good point. So the last part of my lectures is will deal with the Sullivan conjecture, which is now a theorem. What's the setting? The setting is actually, as we saw in the example, counterexample of Claire, it's homogeneous spaces of Lie groups. So we start with the, let's say, I mean, let G be a second countable locally compact group. Let's now T be a closed, and I assume amenable subgroup of G. And now we let mu be G quasi invariant. So this always exists, and as I told you, the measure class is a unique quasi invariant measure, probability measure. On X equal G mod P. Now, if you take a subgroup, so this is the first proposition. Let gamma be a countable discrete subgroup. That means closed subgroup in G. Then the action on X is amenable. So actually, I didn't define action of locally compact group. That this would be true for the action of any closed subgroup. If I didn't define this. And the proof is actually easy. What you do is because the subgroup is closed, I mean, you can find a Borel section for the equivalence classes modulo gamma. So there exists a Borel subset in the measurable subset, measurable section for I'm going to work for the right equivalence classes modulo of gamma in G. So G is okay, gamma omega. And now I need the first. I mean, I want to construct the conditional expectation from LP of G mod P, L infinity G mod P times gamma to L infinity of G mod P. I first construct one going from without any hypothesis. From I call this P1 from L infinity. First, I go. I do this in two steps. First step is doing this gamma, doing this to L2 of G, L infinity of G. How do I do this? I define this for a function f. And G, what can I do? A function in two variables. And is it? So G is going to be. I look at. Yes, f is a function in two variable. Sorry, it's not x. That's why that was. I construct something from this. Okay. And then I will restrict this to the function which are constant on P modulo G. So that would not be a problem then. So that's the first thing. And what do? I write this and where G has, every G has such a decomposition according to the fundamental domain or this omega. Okay, and you check that P1 is conditional expectation is equivariant conditional expectation. So gamma equivariant conditional expectation. So you have just to check that everything is okay, and there is really no problem. I mean, and then I define P2 next from n infinity of x to n infinity. Sorry, I got yes, n infinity of to n infinity of G mod P. So I have to, and here you guess. I mean, here I didn't use that P was. I didn't use anything about P, of course. It just didn't appear actually for P1. But now I want to have such a conditional expectation here. I would like to have a mean to transform a function on G or function on G mod P. I use a mean. I mean, because P is amenable, I can use. I mean, I don't know. Maybe I write F. The invariant mean, which is defined by no. Why? I have to be careful. P2, yes, not actually. Sorry, yeah, I don't have to do this. I can do it already. Infinity of G times gamma. Yes. I define by P2 of F. A function on equivalence classes, and I get it by averaging to P, averaging P along P. So, but averaging P1 of F. So P1 of F is a function on N infinity of G, and I average this along P. Yes, GP, sorry. It should be in G, so it should be GP. So this is now a well-defined function on G mod P, where so M is P invariant mean, left P invariant mean. On P. P is amenable. So this is really a function which depends on the left equivalence class of G modulo P. So that's well defined, and one checks that here also that P2 is equivariant conditional expectation. And now define simply P equal the restriction. I have to restrict simply the function on G mod P times gamma. This is a subalgebra here, and okay, this goes to P. So this is a conditional expectation. Is gamma equivariant conditional expectation. Okay, so yeah, and we get the result that every let's say every discrete subgroup of a group acts amenably on G mod P if P is amenable. And I remarked actually remark concerning, you know, we saw that SL2Z, the action on the projective line, is amenable. Is there something we could say here? In relation with this proposition? Sorry? Yes, that means that I have another proof. I mean, less interesting, of course, than the proof I gave you with the expansion it's much better proof because it was connected with expansion in continued fraction and tells you how the orbits look like. That's much more interesting. And this one is boring somehow. So let gamma equal SL2Z and G equal SL2R and P equal the triangular matrices. Then so G mod P is the projective line, and so get another proof. So a new proof of amenability of the action of SL2Z on the projective line PI. By Möbius transformation, action is by Möbius transformation here. Okay, so here is as the remark is that you have another, but much more boring proof for the fact that SL2Z acts amenably on the projective line. But anyway, it's of course more powerful. I mean, this argument. And okay, now the question: what about non? I insisted here by saying closed subgroup. And if you take now just an abstract subgroup, I mean, countable subgroup. So maybe I formulate a more specific question. Does SL2Q, which is dense actually in SL2R, act amenably on P1 on G or SL2R mod P. And the yeah, I mean that's different story because I mean you see the arguments don't work anymore because we from the very beginning, I mean you see the proof. You had this measurable section, and we are not going to have such a section. I mean that's and the answer is no. In fact, we have more general results. And this is the theorem, which is due to Zimmer, proved by Zimmer. And this is conjecture of Cohn and Sullivan. So when the more, I don't know what, when this was, 1987. So the setting is the following. Maybe I should write this. Yeah, maybe I should write on the next blackboard. No, I start to write. So let G be a connected linear subgroup or connected Lie group. Linear, that means that G in some GLD R. Okay. And let gamma be a subgroup, but now be a subgroup, an abstract subgroup, countable subgroup. Not necessarily close. Of G. And let H be a closed subgroup. Or maybe I don't, it's not, yeah, it's not important actually to have an amenable. So closed subgroup of G. And we look at the action along the homogeneous space with X equal G mod H with quasi-invariant, G quasi-invariant probability measure. Then the action of gamma on X mu is amenable. Okay, if is amenable, then look at the closure of gamma in G. you look at the connected component, this is solvable. So connected component of closure of gamma in G. So for instance, I mean, like this, if gamma, which is this case, I mean, essentially the only case. I mean, if gamma is dense, then this tells you that G has to be dense to be solvable. Okay. And okay, for the proof or sketch of proof, I'm not going to give all details, but this is after Boyard, you know, the paper by 4 people, Boyard, Kennedy, Calendar, Ozawa. Do we have everybody? Sorry? Oh, right, okay. So, okay, the order. Okay, yeah, you're right. Yeah. One has to be concise. I don't know, 2016 or something like that. I mean, this paper is really, I mean, those who don't know the paper, I can only recommend them to read it. You learn a lot of mathematics and very nicely written. It's really a pleasure. You, if you have problem getting your sleep, and you should read it. No, it's probably not a good idea. Or not, it's too exciting. No, certainly you shouldn't do it. But this is really very, very nicely written and containing, of course, nice mathematics. I mean, many interesting facts. This fact, for instance, I mean, which is not connected with our simple group. I mean, they found some connection, but anyway, but it's really okay. How do you do this? So we can assume, for simplicity, but this is really not a problem, because otherwise, assume gamma is dense. Otherwise, you go over to the closure and the connected component. So that's not really. No, I mean, okay, you have to. Okay, so we use actually we have that px is weakly contained by Kuhn's theorem. We know this. And this is what we are going to use, actually. The only thing we are going to use is this. And now, okay, the thing is that, sorry, I just write this gamma because where this is important, that this Kopman representation here extends to G. This is important that it extends. I mean, that's a representation of a continuous group. And for every epsilon, set that to. And the point is the following, and which is actually, I mean, the point. It's not the point, but what you. So it's important to see that this Kopman representation is actually a restriction of Kopman representation of G to gamma. And no, that means that you will have vectors in L2 of x, which are moved very little by elements in the neighborhood, in sophisticated small neighborhood of the unit element in G. And that means because gamma is dense, you will also have some elements in gamma which would do this. But you have to control this. The problem is, you know that gamma is, let's say, you want to prove that it's solvable. You only have to prove by Tits alternative. Essentially, you only have to prove that it's contained. If it's not solvable, you have to exclude actually the fact that it's contained a pregroup, a non-abelian pregroup. So you have to exclude this. This is the only thing you have to do. Exclude the fact that it has pregroups. And in order to do this, you see, I'm coming back to my neighborhood. The neighborhood, you will have elements, vectors, which are, for every vector actually, you will find elements in G which are very little moved by, in gamma, so very little moved by gamma. This seems to contradict the fact that if you have a free group, and because of Kuhn's theorem, you know, the Kopman representation, the regular seems to contradict the non-amenability of the free group. But the problem is you have to control this, and so this is why it's actually not so easy. And the way Breuillard and so on in this paper found it is actually through Tits alternative, uniform version of Tits alternative. So, okay, so for that you be so fix. No, yeah, I don't know. Should I fix a vector, a function? Okay, I fix a function. I fix a function L2 of x with norm 1. And sorry, I decided to use a little bit more on the, and define for epsilon. Let's, so I'm coming here. Okay. Define this U epsilon on the neighborhood of G, of the unit element in G with Tx G F minus F smaller or equal to epsilon. So two norm. And set and S epsilon equal U. So these elements which are in gamma, which move, okay, I don't write it, but okay. So the first step is that there exists epsilon such that the subgroup generated by this is dense in, is amenable. And this is okay. Otherwise you get that all this for every is non-amenable for every n. And now here I'm saying a little bit more later, maybe by uniform Tits alternative. So this is something which has been proved by Breuillard and Gerlander. And I don't know, 2010, something like that. So there exists, on the other hand, so there exists a number, which depends only on D, such that if you take any, this is true for any, actually, any subset S. Sorry? D, G is GD here. So it doesn't depend on S or any subset. So this is the uniform thing. I will say maybe a little bit more, but this is the consequence of this. For every function in L2 of gamma with norm 1, we have a uniform, if you want, a uniform Kashtan bound for the regular representation, or a non, let's say, a uniform non-amenability. Uniform. So this is the point. The point is uniformity. So if this is, if you have a non-amenable subgroup, you get a uniform amenability for in GLDR. It doesn't depend. Depends only on you take any subset of matrices and you get if the group is not amenable, then all non-amenable subgroup are uniformly, there is a uniform bound for the Kashtan constants for the regular protein, or if you want, they're uniformly non-amenable. So this is really remarkable. And so since now you see this is weakly contained there in the if you restrict, weak containment is preserved. You get so this the pi x restricted to any subgroup of lambda is weakly contained in the regular, and so this implies so there exists a gamma in so for this F such that for this F such that you actually have it for the so this is simply playing with the fact that you can approximate the coefficient of pi x by coefficient of the regular, and so you're losing a little bit, but that's not a problem. But you get it for bigger than epsilon over 2. But anyway, and this is contradiction. This is a contradiction. If you take n sufficiently, this is a contradiction. If n if 1 over n, if you take n sufficiently big, such that this is smaller than this one, then it's okay. So you see, you have this epsilon d, which doesn't depend on anything, and you take n sufficiently large, and you get this thing. And okay, and the second step is G gamma is sorry, G is amenable. So since now G is connected, and I mean G is generated. G is equal the sum, the powers is generated by U, and U is U was U epsilon. So there is an epsilon. Take this epsilon. Take epsilon, equal 1 over n, smaller than epsilon b. Okay. And okay, and then you see you have this, and so then gamma is generated by actually u epsilon. Yeah. So sorry, not gamma. Yeah, gamma. Yeah. So gamma is amenable. So yes. What did I prove? Okay. So yeah. Okay. Is amenable by its alternative gamma is residually solvable. And now since G equal is gamma is dense and G is connected, this implies actually this is easy size implies G is solvable. Okay, that's end of the proof. Yeah, you see, it's a nice proof, and it's due to these people here you mentioned. But it's based, I mean, there are two ideas. The first one is using Kuhn's theorem, this weak containment of the Kupman representation in the regular representation. And the second one, of course, this is the crucial tool, is this uniform Tits alternative. I mean, one way to formulate this is in GLD, you find an integer big N, depend only on D, such that for any set of matrices, either the subgroup is generated by this matrix is okay, let's say amenable, in this case residually solvable, or it contains a free group. This is the usual Tits alternative, but now a free group which is I mean, you find two elements which are of length with respect to S, at most S, N, such that they generate a free group. So you find in ball of uniform radius, you find generators of a free group. So this is the uniform Tits alternative. And this is exactly which gives you this here, the uniform non-amenability, if you would like to call it. And okay. So I guess I will have to stop. I'm already over time. Thank you very much.
What there was meaning before that with the characterization of the
Yes, yes. You think you so the converse, right? Yeah. I don't know, but I heard that it was somehow